coming today, everybody. So Novi Labs, we're a company. We've been around for about 8 years now, and we really work in the data science, AI, ML space within unconventional oil and gas is our focus. We have two main business lines. One is that we go out and collect data from all the state agencies like IHS or Enverus. And then the second, more relevant for today, is that we have software for training machine learning models for forecasting horizontal well production. So we have a lot of learnings from that I'll try and impart to you all today. So what do I want to get across? First, I want to introduce some basic ML concepts, machine learning, data science, with a focus on practical implementations for onshore oil and gas development. I'll discuss some common pitfalls that you might run into for framing problems, preparing data, and reviewing results. And I do like pretty pictures. Where did Trey go? I do like pretty pictures. There he goes. I do like pretty pictures. I will show you some cool examples from the Midland Basin. Can't get me in front of the screen without doing that. So to get us started here, there's a lot of folks will use the terms AI and machine learning interchangeably. Some people will say that machine learning is a subset of AI or vice versa. I don't really care about the distinction between those two things today. Mostly today I'll be saying machine learning. But at the core of both of these really is that they find and apply patterns in the data. So you could think of them, they're not, in almost all cases, not taking a physics-based or first principles-based approach, but rather learning from what the statistical elements are present within the data. And then the other thing I just want to let you guys, quick little sense check here, is that within oil and gas, we're not really big data. I mean, there are some little corners of our industry, but for the most part, we only have 200,000 shale wells in lower 48. So compare that to the number of clicks that Facebook gets every hour, right? So they, if you're trying to optimize clicks for Facebook, they have a very different volume of data to be working with. So within the oil and gas industry, there's obviously lots of different things that you can go after with artificial intelligence and machine learning. Here's some just kind of sample things here to get your wheels turning as we walk through our examples later in today's talk. Maybe you want to do something operational like optimizing your ESP size. Maybe you want to forecast oil and gas production for horizontal wells. Note the red rectangle around that one. That's what we're going to be talking about today principally. You could predict pipeline failures. You could automatically condition, clean, and interpret logs. You could capture data from drilling reports. You could optimize your completions design based on the subsurface characteristics, and many, many, many more things beyond that. But those are just some things to give you some rough ideas. So, at the very beginning, you have to frame your problem and do some exploratory analysis, and that's what I'm going to start here discussing for us today. So here are some questions that I have for you to ask yourself before you begin any artificial intelligence machine learning application. And my role at Novi is I'm a product manager, which means that I work with our software engineers and data scientists to match our technologies with possible benefits in the industry, which if you're trying to do this within your oil and gas company, you're kind of going to be a product manager for your particular problem or use case. So we'll put on our product manager hat for a lot of this. First thing, what are you trying to accomplish? I know that's pretty simple, but it's helpful. Just think about it, write it down. What's the value of having a better answer? Are you saving time? Are you improving your economic returns on your wells? Are you reducing risk? Those are very important to think through at the outset. What data do you have access to? We're going to spend a lot of time talking about that today because that drives everything in this domain. What is your team's technical capabilities and capacity? And be honest when you're asking yourself this, about what do you guys really have the time for and the expertise for? Is this a one-time problem or is it ongoing? You just need one answer today for a particular design, or is this, every day, every month, every year? And finally, who is my end user? For whatever I'm doing, whatever I'm generating, you know, an alert, an answer, a recommendation, who's going to be consuming that? And going a little bit deeper here, 3 more things for you to think about. 1, how do you prove that it's going to work, whatever you're doing? Is it a capability you can demonstrate? Who do you need to convince? Is it management, executives? They have to get on board for any of this stuff. What do your end users need? Is certain formats, what delivery cadence, what interface are they going to be consuming it in? Are there any other tools that they're going to need to take your answers in? And then maintenance and upkeep, and this is a big one. Who will be responsible for running, monitoring, and updating your solution? What will be required? And this is, a lot of times people don't realize how much time and effort it is to keep a data science software running, you know, every year, every month, every day. There is a lot of updating libraries and things like that that can really bite you if you're not ready for it. So against that backdrop, let's now take a look at the solution space. And I've kind of categorized these into 4 buckets. There's a little bit of a continuum here, and you know, there's obviously combinations. But over on the far left, I have data exploration and simple modeling. This is just doing stuff like making cross plots, histograms, showing stuff on a map, maybe some simple linear regressions. Every project that you do within the AI ML space should begin here, and most should end here. You don't always need, you know, a Ferrari. Maybe a wheelbarrow is enough for certain projects, right? The nice benefits of this is that you get some basic understanding going. It's hard to mess it up, and there's really no substitute for doing this type of work. The cons are there are limitations to how far you can go with Excel and Spotfire. Next here, I have domain-specific solutions, and these are partnering or licensing solutions from vendors that are focusing on very specific problems within the oil and gas space or whatever domain you're working on. And these are very specific, ready for that particular problem, with a lot of domain knowledge baked into the solution. So that's a lot of the benefit from them. Usually they're going to be the least work out of all of these options, because they are focused on solving everything within one particular problem. The cons are oftentimes you have less flexibility than if you're building things custom or you know, working with one of the other partners. Third bucket here, enterprise tools. These would be working with companies like Amazon, Microsoft, Databricks, and these are large scale, enterprise ready. Everything you could want under the sun, these companies offer somewhere in their vast labyrinthine bowels or whatever. They've got something to work on it. The cons for this are that it's usually high cost, requires a lot of custom work to meet your needs, might take a little time to get up to speed here. So really anything in here is kind of half custom. You know, like I'll give you one example. Amazon certainly has great algorithms for forecasting production. You know, they could be adapted for forecasting oil and gas production, but I don't think they have any spacing calculations. You know, so that'd be something you'd have to build yourself within Amazon or partner with them on. And finally, here I have custom built in-house over on the far right. And there's lots of tools that you could use for that, like Python. There's open source libraries like scikit-learn. Lots of great algorithms here that you can just use, right? But it's a lot of work for you to do that. You could build exactly what you need, but it can take a long time. It can, you know, if you end up throwing 3 FTEs at something, like maybe you're better off licensing something from somebody else on a cost basis. And then the other thing here, this is huge, the maintenance burden. And beyond just spending all your time, you know, going through and updating to the newest scikit-learn and then fixing the dependency with some other package that you're using, it's also what happens if the person who built your thing leaves. That happens all the time. Have a succession plan around that. If there's only one person who knows how to run the tool, you're very exposed. Okay, Let's move on to exploratory data analysis here. This is where you should always start. And this would be an initial assessment. What type of data do you have? What's its structure? What data types do you have? What size of data do you have? Are there any initial patterns that you can go off of? Do you want to do some initial data cleaning? Do you have any errors or inconsistencies, missing values, duplicates? And then visualizations. And these are very important. And I want to highlight a few things within that. I have to make sure that we hire a lot of reservoir engineers or other folks coming directly from the industry. And a lot of times, if you're a technologist and enthusiastic, you kind of want to jump to the fanciest possible way of solving a problem. And really, you should just be looking at stuff on a map to start with. And so many times we work on some problem and somebody spends too long trying to code up something, and then you just plot on a map and there's your answer. But a few things here that I make sure that we always take a look at. One is a time series analysis. So obviously all production data is a time series. The well starts producing in 1 month, and then every day, you get new production data. But I like to look at other things over, every year, every month, every quarter, something like that. This, for example, would be the average 6-month cumulative production in the Midland Basin. So just from taking a look at this, you can see that the wells were a lot worse back in 2013 than they are today. So that structure should inform your analysis when you're forecasting production. Maps. The map that I showed you at the beginning, this is actually spacing density in the Midland Basin. So every well stick that you see here is colored by how many neighbors it has. The red wells have the most neighbors, the blue wells have the least. And what do you notice? The densest development is in the northwestern part of the basin. That also happens to be the highest rock quality and the highest performance. So that data structure right there is going to inform the approach that you take from a data science perspective. Two other things, cross plots and histograms. Cross plots, everybody knows these. They're classic for a reason, but you should be doing a lot of them. How are the variables of interest related? Get your sense of all that. And then histograms, look at distributions of your variables. What's the minimum? What's the max? Is it bimodal? Is it normally distributed? I also like to say, check into your formation and operator labels. Here you see we're mostly Wolfcamp A, Wolfcamp B, and Lower Sprayberry. That's almost everything in the basin. That's good to know. You could also pick up if there were other formations here that were mislabeled. That would be a good place to catch it. Okay. Now we'll move on to data selection and preparation. I always like to, in these type of educational settings here, remind everyone that data science is 80% data and 20% science. And you should always have in mind before you start any AI ML project that working on the data is going to be the majority of your time and effort. Running an algorithm and maintaining things and analyzing and all that is a small portion of the overall effort. And even at Novi Labs, with fancy custom-built solutions for making data preparation as clean and easy as possible, we still spend most of our time on the data side working with customers. So just keep that in mind in your planning and manage your own expectations, that you don't get, so far along into a certain project and you're like, man, why am I still working on the data? I haven't even got to the, building a model yet. Well, that's how it goes. So typically, you like to split the data into two categories here, right? Features or, variables or independent data, and then your dependent variables, your targets. So targets, what you want to predict, features, what's going into the model to make the predictions. So over here on the left for, our use case here that we're going into today, forecasting horizontal well production, you have stuff like geology, oil in place, permeability. You have completions variables like proppant mass, fluid volume. You have operational things that you could have in there, like what's the artificial lift, et cetera, et cetera. And then over on the targets, it could be something like cumulative production 1 year, peak rate, gas oil ratio, maybe predicting a whole production profile, decline, B factor, EUR. One word of caution here, B factor and EUR and other things like that will have some amount of interpretation already baked into them. And so That doesn't mean you can't use them, but keep in mind that your model may be predicting the interpretation rather than predicting the data itself. So maybe you have, let's just throw out a hypothetical. One set of EURs are generated by a reservoir engineer who's a little more conservative. One set of EURs is generated by another reservoir engineer who's a little more optimistic about what the wells are going to produce. Your model might end up finding its way to which reservoir engineer was generating the EURs, right? Whereas if you're doing 1 year cum oil, you don't have to worry about that. I've seen it happen. So for this particular model, we used a lot of the kind of classic variables over here, features for our predictions, like I just mentioned. And we predicted 3-year production profiles of oil, gas, and water. Yeah, wellhead data. Now, another word of caution: target leakage. So let's say I want to improve my pre-drill AFE forecasts. You know, we were way over on those last ones, and we drilled those wells that ended up being duds. And by golly, we're not going to waste our money again. Okay, great. That sounds good. Let's use some machine learning. 3-year cumulative oil, that's a good one to try and predict. What happens if you include the 1-year cumulative oil as a training variable? Your model's probably going to have its error rates go way down, which might look really good. You know, hey, our R squared went up to 0.95. This is amazing. Let's all go get our bonuses and go to happy hour early. But here's the problem. You don't know the 1-year cum when you're making your pre-drill AFE forecast. So this is a very explicit example, but I see folks kind of walk their way into this all the time and get unrealistic expectations about how their models are going to perform, and ultimately get bad results when these things go out into the wild. So we kind of try and prevent. We have some guardrails in our software for preventing this, but it happens all the time. Now, this one's pretty explicit, but what about using peak rate? What about using a water cut map in which the water cut of wells that you're forecasting are included in making the map? There's more subtle ways for this to happen, more than something quite as explicit as like a 1-year cum put into your 3-year cum model. So just keep that in mind. Data preparation. So depending on the algorithm or the class of model that you're using, it may be more or less sensitive to the quality and cleanliness of your input data. And we principally use random forest-based models for most of our forecasting. One of the reasons is that they tend to be robust to messy data, and other ones are more sensitive. But I'll give you one example. Actually, we've just added in a new component to our models that incorporates like a linear regression component for scaling some individual items. And we have discovered, because it totally threw off our models, that we had some duplicate surveys that snuck into our data that caused some wells to look like they're only 20 feet apart from each other, yada, yada, yada. Well, you know, the model that you use will require different levels of cleanliness. So we're having to kind of try and use cleaner data now than we used to. But anyways, that's just a little sidebar. But as you go through your data preparation, some common things. 1, eliminating invalid data. Negative lateral length. That can't be real, but I have seen it in operator data that they upload into our system. So you want to get rid of that. Ensuring unit consistency. This is a huge one, and it really matters. A common one here would be completions fluid of gallons versus barrels. Even in your own data, you might have that messed up, let alone your data versus IHS versus Enverus versus that stuff you traded for. Could all be in different units. We once ran into a problem in working with the South American operator, the Vaca Muerta, where we were under forecasting their wells by 25%. And this caused some consternation. Normally our models are very accurate, especially in the aggregate. And we spun our wheels on this for a long time. And we ultimately figured out that our data scientists who built the model had looked up the conversion unit from gallons to beer barrels, not to oil barrels. And it was a 25% difference. So that ended up costing us a $200,000 contract. So, I mean, that wasn't the only problem, but it certainly didn't help. Anyways, so this stuff, it's a pain, and it's a huge pain, but it really does, you do need to pay attention to it. You also need to alias your categorical variables. And this one, another very common issue, Wolfcamp A versus WCA. So if you're a geologist who is doing the interpretation in Martin County, call it Wolfcamp A and spelled it all out. And then your geologist doing Howard County, called it WCA, and you don't alias those together, the model will think that those are two different formations. You have to clean that up. Eliminating duplicates, addressing empty values, those are important. And then in some cases, you may need to normalize the variables or apply other transformations required by your algorithm. So that's going to be algorithm specific with whatever they need. Okay, feature engineering. This is taking your raw data. You can actually improve your model performance, in some cases quite a bit, by applying additional transformations to the input variables. So one example, if you go from proppant to proppant per foot and you're predicting production, that can be really helpful. You can take a log of that. You could take a log of that and divide it by the spacing to the nearest neighbor. You can really get creative here and can get significant improvements to your results. There's also a concept called dimensionality reduction. So let's say you're a geologist interpreted, I don't mean to pick, I'm a geologist. I'm not trying to pick on geos, but I'm sure we have a lot in the room here. But let's say you have 35 different awesome variables that you've interpreted for your area. There's probably a lot of correlations between those. Some of them might even be used to calculate each other. And that's too much for the model to deal with in most cases. So you may want to turn those 35 variables into 5 principal components. And there's various techniques for doing this, in addition to just principal components analysis. It can give you some nice results, principal component analysis or dimensionality reduction, but it does tend to make the models less interpretable. So, let's just take an example. If your model says, hey, water saturation is really important to my sprayberry production. Okay, great. Yeah, I understand that. Everybody knows how to interpret that. But if your model says that GOPCA2 is really important to lower sprayberry production, that's a little bit less clear what that really means. So you may struggle a little bit downstream of all this in getting buy-in from executives or managers or whoever is involved in the project. If you are doing time series analysis, like let's say you're trying to forecast when your gas lift is going to break down, or when how much your wells are going to come back online after they've been shut in for 6 weeks, things like that. You will oftentimes want to do some specific engineering, like let's say a rolling window of some past production, rather than just taking the noisiness of the data. Let's put in the average for this 30-day increment, something like that. You could also incorporate other things like what was the production a year ago? How much have I declined over the last 6 months? And other things like that are really useful for time series data. We incorporate some of those when we're working with PDP wells. Training data coverage. This is a big one. So depending on the algorithm that you're working with, but most of them usually require all of the features to be filled out for every well that you're predicting, or every row. Now, there are some ways you can get around this, but for the most part, this is data analysis. You need to have the data for the items that you're working with. So let's say TC oil and gas here. We have a few wells. We know the cluster spacing, proppant intensity, porosity, interwell spacing. Great. But I have another operator who's in my neighborhood who I would like to use their wells for my forecasts, and I don't know their cluster spacing. This is not public information almost all the time, in almost all cases here in lower 48. So it's going to be difficult, if not impossible, to use this in my model. So just keep that in mind while you're getting started, that there are limitations to what data you can work with, because you need to have that across most of your data set. So expanding a little bit beyond that concept, for geology data, you need to ask yourself, what is the extent of your grids or of your 3D model? And this is, I mean, both spatially and with depth, I guess, X, Y, and Z, if you will. So, you know, if your model is only for the wolf camp, you might struggle to predict the Sprayberry or the Bone Spring, right? You won't be able to use that data. If your model only covers eastern Martin County, you're going to be out of luck for predicting other areas, right? And the other thing that I want to note here is you can't really, like, just by throwing, 40 more attributes at the model that you calculated from your seismic inversion, like, that's not going to make up for the fact that you only have 25 wells in your corner of, Martin County where you got the 3D survey. You can't make up for it by just adding more and more data about those wells that you already have, for our particular example. I mean, it's great. Like, I would love to have a P-wave acoustic impedance over the whole Midland Basin, but, good luck. Production, how old are the wells with modern designs? That's important. Completions, beyond proppant fluid and maybe sometimes even stages, how many wells do you have that data for? Spacing, how many wells have you calculated things like distances to neighbors, parent-child relationships, all of that. If you have somebody going through and doing this by hand, that's probably not going to scale very well. Which, another fun sidebar here. Once we were challenged to a spacing bake-off against a company that was calculating spacing themselves, and it was just by calculating spacing. I mean, there was a dude in ArcGIS using the ruler tool and going through and just measuring all of his wells. And the first 40 looked really good, and numbers 60 through 100 started to really fall off, and he did not get to the whole basin. So, hey, he did really good. Well, before he got tired of all that. One other thing here, just to mention, for the data coverage, it's not just about the data coverage for your training data. It's also the data coverage for where you're going to be applying it. So let's just like give you one example. You might have a great model that covers Howard County, or you have a great model that covers Martin and Howard counties, but you're going to be looking at a BD deal in Midland County. Well, you can't use that. You can't use that model for evaluating Midland County. Or let's say you have a guy going through and doing your spacing calculations. Will he be able to do that for every possible hypothetical well that you're going to be considering in the future? Because you're going to need the same data for the hypothetical things in the future that you want to use your model for compared to the training data. So that consistency is really important, and that's a common place where people will get tripped over themselves. Okay, next up, which data set will you use? And here I've split this into two kind of categories over here, because this is usually what we end up seeing is a lot of our customers will split up the data this way, where you might have one regional model, which incorporates a lot of public data. Maybe it's the whole basin, maybe it's half the basin, something like that. And then maybe you have another model that's more of a local model where it's your own operated data, maybe some trades you've made. So this might be an area where you have better subsurface interpretation, a lot of wells with dailies, whereas for regional or public, maybe you're limited in the completions data you can use. The geology is more sparsely interpreted, etc. So a lot of times we will see our customers end up building two different models that end up having different use cases and strengths and weaknesses. Now, a little bit on two very special variables right here, operator and formation. So these deserve their own slide for a call out here, because they are particularly data rich. So let's talk about operator. You can put this into your model. You're probably going to be more accurate than if you leave it out. Now, why is that? Operator has a lot of information that is implicit within it. So Where's their acreage? What completions design do they use? What operational choices? And a lot of that won't be public, but it is implicitly in the operator. So if you include operator, your model will probably be more accurate, but it might be less useful and less explainable. So if you are a midstream company trying to decide on, I don't know, building a gas plant somewhere, all you care about is accuracy, you probably want to include operator as a predictive feature in your model. But if you're trying to optimize your fluid intensity, operator will probably mess up what the model is learning about the completions design, because a lot of that statistical signal will be sucked up into this label here. Formation is another variable that is really information rich. So everything, like, there's so much information in that. There's the facies, whatever facies you're looking at, depositional facies, mineralogy, geomechanics, richness. All of that is implicitly coded in the formation beyond what you can ever, even with all the data in the world, there's something very specific about saying this is this formation, right? And so in our experience, including formation as a variable is generally a better idea because there is so much useful information about that. But if you do want to have more of like a first principles understanding of the rock properties, you might want to leave it out. But your model will probably be better and it'll be more useful. And the other thing to keep in mind here is that in some cases, we usually see this if formation is not included. The model will still try and figure out which wells are which formations, even if you don't tell it that explicitly. So Wolfcamp A and Wolfcamp B have such dramatically different performance that if you include thickness as a variable, the model will just say, it's more than 250 feet thick. It's a Wolfcamp B. Performance is worse. So that's just kind of how it works in the wild. Feature selection and elimination. So you have, let's say you're forecasting horizontal wells in the Midland Basin. There might be 400 different columns in your giant well header table that has everything joined into it. What are those you're actually going to use for your forecasts? So there are tools out there for going down from that list of 400 to a list of 12 or something like that. And usually you will want to be using fewer variables than probably your intuition. So a lot of times we will suggest, at least with our typical data sizes and model architecture, somewhere between 6 and 15 or 20 variables is a good one to use. And beyond that, the models just can't really make much use of that additional data. So we have a tool for automatically selecting the features to use. There are plenty of other out-of-the-box solutions here, depending on whether you're working with Amazon or scikit-learn or whatever. But these are kind of used with a grain of salt, rather than put entire trust in it. But the way that these often work is the models will just go in here and try many different combinations of these variables and see how much data each one is adding and how much it's reducing the error scores. But in our experience, we'll typically see, that might be useful as a initial exercise to get a sense of which variables are important. You might see some surprises there that create some ideas that maybe you haven't thought of before. But for the most part, hand selecting the variables is usually better because it aligns with your domain expertise. You might already know some stuff about what's going on in the area just from intuition you've developed working there, but also that'll make it more acceptable downstream when it's being used in the wild if, you guys know all 12 variables that it's using. Okay, any questions so far?
So when you were talking about on a few slides back about the operator and formation, the pitfalls there.
Yeah.
Is it just as simple as I guess, or maybe you've already done it, like do you run run it one with, one without, just to see how much divergence you're having?
Yeah, you could definitely that's a good way to do
Toggle
it.
them on and off, if you will.
Yeah, for sure. I mean, you can do that we will do that by hand, kind of, for a lot of times for this type of an investigation. And depending on what your use case ultimately is, that can be really informative as an exercise. Yeah, definitely. Yeah, we'll toggle on and off. Hey, what happens if I include or don't include a gas oil ratio or a water saturation or depth or all those types of things is really can be useful. Okay, let's go into some algorithms. So Mike already gave us a little bit of a briefing here, but we'll go all the way back to the classic multivariate linear regression. So a lot of times when you hear folks say, "Oh yeah, we do multivariate analysis or we do MVA," this is what they're talking about. And you're trying to predict your y using mx plus b, however many m's and x's you have going into your model. And the nice thing about this is it's super easy to interpret. You literally have a coefficient applied to your variables. So you want to know how much proppant intensity impacts your oil production? Boom, there's your coefficient. Super interpretable. Downsides, this only captures linear relationships. Now there are multivariate nonlinear regressions that you can do, but those get a little more complicated. And they also are not well suited for capturing multiple dependence relationships. So what happens if I tighten my spacing and upsize my completions design? There's going to be an interaction there, hypothetically. So these are honestly not a bad place to start and have a lot of utility, but make sure that you understand what you're getting into when you're using these, because if you just blindly use them, you can end up overcapitalizing because there's no diminishing returns built into those. So we'd run into that. Decision trees. So these are what we use mostly. So these group and split the wells by their input variables. It's kind of like a relatively straightforward. Everybody in here who's built an analog type curve. Yeah, probably almost everyone in here, right? You're just going through and grouping wells that you think are analogous, and that's kind of what decision trees do, except they build, they're not just building one set of analogs, they're building thousands of them across a random forest, would be across thousands of trees in a random forest. The nice thing about these is they're robust to missing data. They're very accurate on the tabular data. And they're also better with, can be pretty good even with smaller data sets like what we have in oil and gas. And then of course you have the neural networks, very powerful. Almost everything on the history of AI that Mike showed you is in this neighborhood over here. But as he said, these are more suited for things like image recognition and these large language models, text generation, interpreting things, digitization. Tabular data is generally better for tree-based, although that's a generalization. There are versions of each of these algorithms that could do well on those other tasks. Measuring model performance. This is very important. Within the data science field, there are common principles for measuring performance, and typically you want to have some kind of a test set, quote unquote test set here, where you're holding out the training data. So let's take all the training data that our model could be trained on. Let's take 20% of it or 10% of it or 50% of it, and we'll go put it over here. We'll train the model on the bulk of the data, and then we'll predict the holdout data, and we'll see how it does. That's great. For this particular model, we used an 80-20, so pretty standard here. We did a random, but we kept our pads lumped together. So if you do split up the wells on a pad, just kind of something to keep in mind here. If you split up the wells on a pad, your model might look better than it actually is, because let's say you have 4 Wolfcamp A's on a pad that you drilled. You might have 3 of them in the training data, those are probably going to be really accurate at predicting well number 4 that's in the test set. So this can make your models look a little bit better than they actually are. And the same thing applies. This is splitting it into training and test data. I didn't go into the bonus session for the afternoon. Didn't go into this one in the morning. Typically, when you're training your models, they are also splitting the data into bits and pieces while the models are building themselves. Those are called cross-validation groups. So we do the same thing for a cross-validation. So that's another thing to keep in mind. In addition to just the test train split, is the cross-validation split. Okay, sidebar over. There are some other methods for this, and depending on your use case, these might be more appropriate: time-based and area-based. And the time-based is our favorite for working with operators in getting acceptance for the models, because it gives you kind of a simulation of a real world scenario. Let's wind back the clock 2 years and see how the model would have done on all the data, using all the data from before that to predict the last 2 years. And you get bonus points if you can actually align that with, a budget and planning cycle or sets of AFEs or something where existing forecasts had been put in by engineers so that you have a comparison to an existing method. Whatever that happens to be, we're talking about horizontal well forecasting, but whatever your class of problem is that you're going after, think about this as a framework. The benefit of doing it this way is that you're honest with yourself about how accurate the existing method is. And in our experience, operators are not always honest with themselves about how accurate they are. So let's say our models are off on the average well by 15%. Does that sound bad or good? I don't know. Some people might say, hey, we get within 5%. Like, can you really? And if you actually go back and do this exercise, a lot of times that's not the case, and they are way less accurate than they think. So just to give you some concrete numbers here, this is one particular error metric, the median absolute percent error. So this is a good way of looking at the per well error. So it's the predicted minus the actual. You take the absolute value of that and you divide it by the actual. Simple. And then you take the median of that distribution. So here you see, 4-day, 90, 180, 360 out to 3 years. Our distribution of absolute percent errors for our Midland Basin basin-wide public model. So we got 20% error, pretty good for a basin-wide public model. In our experience, for this type of forecasting problem, if you had a couple thousand wells of only proprietary data where you don't have any leased well allocation and you have all the data you could dream of, you might get that down to 14 or 15%. And most operators on their reservoir engineering forecasts would be somewhere between 18 and 35% error for this. But that's just one metric. Another good one to look at would be, this is well level error. What's the aggregate error or the bias? So sum up all the predictions and divide it by the actuals. So is there a tendency to over or under forecast in the aggregate? That's also good to know, in addition to this idea of the per well errors. Next up, we have explainability, and important subtitle here. This is more important than error scores. So in our experience, having done this in every shale basin with companies large and small, well-run and dysfunctional and everything in between, explainability and understanding how the model is working is more important than actually seeing how accurate it is. So there are a few ways of understanding and explaining the model forecasts. I've shown 3 of them here. There's another dozen that you could go after, but you have feature importance, which variables matter the most. That's pretty simple to understand, and most data science toolkits and algorithms will have some version of this already built in. So for tree-based models, a lot of times there might be something that will change, put a variable in, pull it out. see how much that changes the forecasts. Maybe you'll put some errors around the variable, like just noisy it up a little bit and see if that changes your model error. There's some ways. There's also partial dependence plots. So let's hold everything constant and vary just one variable at a time to see how that changes the predictions. And then our favorite, Shapley values. So these are estimating how much each individual feature impacted the model prediction. So we're going to spend some more time on these. One important caveat before we go further on that, any of these methods can give strange or inaccurate results when your variables are highly correlated. So let's choose a porosity and permeability example. You calculated permeability using porosity as an input. That's very common, right? If you put both of those in the model and then you do this thing over here on the left, hey, let's remove permeability. If porosity is very, very highly correlated with permeability, the model results aren't going to change by removing permeability because it's adding no additional information. So your geologist might freak out when they see that permeability is the least important variable. Of course, permeability matters. It just doesn't add any additional information here. So you have to think a little bit differently when you're interpreting these results. Okay, Shapley values. So this handsome guy here is Lloyd Shapley. He was a mathematician and was trying to answer the question, if a bunch of people work on a group project together, how much credit should each individual get to the group outcome? And this guy ultimately won a Nobel Prize in economics. And this is all-time quote right here. I consider myself a mathematician and the award is for economics. I never in my life took a course in economics. I don't know what he was trying to say with that, but pretty awesome. So this guy was active back in, I think, the 50s and the 60s, and his research was later adopted decades later by the machine learning community to, rather than team members on a group project, predict the contribution of the features on the model prediction. So it's the same basic concept mathematically. So shout out to this guy for his work. And I might be one of the biggest fanboys of Shap values in, it feels like, in the world, because of how much time I spend working with this type of data. And I ran into a guy a few weeks ago whose name was John Shapley. And I go, you wouldn't be of relation to Lloyd, would you? And he did not know who I was talking about. So that was a big disappointment. Anyways. Okay. So for our particular model, and you may not, we'll see, maybe not all of you can read these. I could barely read them here, but so sorry about the fonts. But I've taken our Shap values and I put them into a tornado chart form here. So on the y-axis, I have the different features that went into my model: lateral length, depth, formation, gas-oil ratio, closest 6 neighbors, parent distance, fluid intensity, lateral neighbor distance, proppant intensity, etc. And the ranking of the variables 1 through 16 here is how important they are, and that is judged by their relative contribution in the aggregate. So on the 0 line here, that is no impact. And this is showing you, it's not exactly, but you can imagine each of these little dots as a well or a group of a few wells. And for each of them, you know, hey, these wells over here were super long laterals, and so they got plus 40% oil relative to the average well in the data set. These wells over here were really short, so they got minus 30% oil relative to the average. So that's how you can interpret this. If it's a red, that's a high value for that individual feature. So longer laterals, more oil. If it's a blue, it's a lower value for that particular feature. So lower gas oil ratio, more oil, higher gas oil ratio, less oil in the forecasted 3-year cumulative oil production. So the other thing on these is the width is the distribution, the amount of wells at any point along this chart. So these are very useful. Shap values for the Midland Basin oil model. This is another way that we like to visualize them. This is nothing that we've invented here. This is a common way. This is called a dependence plot. So we have proppant intensity on the x-axis, 1,000 pounds per foot out to 4,000, and the average impact in percentage oil barrels here on the y-axis, minus 25 to plus 30%. Each dot is a well, and I'm showing you gas over here on the left in the red and oil on the right in the green. What you can see here is, hey, I've got more or less a linear relationship until I get out to around 1,800 or 2,000 pounds per foot. And then it kind of turns over in diminishing returns, just like you would expect. Whereas for gas, it kind of goes up a little bit further before you start running out of any additional gas. So the model is picking up an additional difference here in the gas oil ratio change out of these more intense completion designs, where beyond a certain point, you're not improving your oil recovery, but you are shifting your product mix. So here's some more, and this is, I'm a nerdy geologist, so I had to get this one in here. It's one of the cooler things I've seen from our models. But this is showing you the impact, the SHAP impact for the total organic carbon percentage here on the x-axis, and then clay volume over here on the other x-axis. And each dot is a well colored, in this case, by the formation. So here for the TOC, below 2%, it's principally my sprayberry zones up, and my Deans up a little bit higher in the column here for the Midland Basin. For those of you who haven't worked it before, those are closer to they're kind of a semi-unconventional, or whatever you want to call it. Whereas Wolfcamp's a little bit closer to a true unconventional play where you have the source rocks interbedded. So for the Wolfcamp, TOC matters. But for the sprayberry, it matters less because you have higher permeability and a larger role for migration from other zones in charging the reservoir. Whereas no matter where you are, higher clay volume is bad. So 10% up to 40%. And I'll give you a little free lesson here, free nugget after having built these models in basically every basin. Almost always we see the clay volume is important, and more important than probably people think, and oftentimes more important than fancier variables like brittleness that are generated uses clay volume as an input. So I don't know if that means that our brittleness calculations collectively are wrong, because I've seen this across dozens of operator teams with different calculations, or if there's something else special about clay volume independent of the brittleness of the reservoir or the frackability of the reservoir that is important. I don't know, but it is nevertheless interesting. Now, word of caution on geological variables, and this is very important to acceptability for your models. And you can imagine if we're not let's say we're not forecasting horizontal production, instead we're forecasting when my pipeline is going to fail. You can kind of translate this concept of, what happens when the model shows things that you're not expecting, right? It learns counterintuitive trends. So what I have here for you is the hydrocarbon pore volume height on the x-axis and the SHAP impact of that on the y-axis. So what you see here is, as I increase my HCPVH for my oil, my production goes down. That's surprising. What's going on? I thought more hydrocarbon volume, my oil production should go up. This model is dumb. This model is broken. I don't like it. But in reality, what's happening is that just means that you're getting gassier. The total hydrocarbon produced is probably just higher and showing a nice trend. But the model has learned, in this case, in the Midland Basin, the higher resource density is actually in the southeastern part of the play that has lower reservoir deliverability, lower pressure, whereas the deeper part of the basin in the northwest tends to have much better production, even though just from a pure oil in place or barrels of oil equivalent in place, it looks quite a bit worse. So what we have learned to get around that and to build acceptability is we actually just start with a rock quality map when we're reviewing our results. So for this, we call this GeoSHAP. We didn't coin that term, one of our customers did. But what we do is we just take the SHAP values for every individual geological variable and sum them up. And so here you see that for the Midland Basin. It does a pretty good job of identifying the sweet spots, even without nobody told it what the relationship was between all those individual variables and oil production. It doesn't have any physics-based understanding, but it gets there. So this thing, you show this to a geologist, they go, that's a pretty good model. That's learned it pretty well. That is where I know the hot spots are, whatever it is. Whereas if you lead with this, you get some distrust. So we lead with this, and then we go to that, and they're like, oh, well, I guess that makes sense. So just a little bit of learning, and so if you're in if you're forecasting or trying to use a model for some other task in the industry, just think about how you're going to get around counterintuitive relationships that the models learn because for one reason or another, like you have some, unknown variable, confounding the results that's not really captured in your training data. You could also just not use hydrocarbon pore volume height or whatever it is. You just take it out of your model. We have also, we've gotten creative with some of this stuff. We have fun with it. So this is a really useful way of visualizing the explainability data from these models, not just for forecasting oil production, but in a historical sense, looking back at how things have changed over time. So this chart is showing the aggregate contributions of completions design changes, differences in rock quality drilled, lateral length, and spacing and parent-child relationships year over year over year in the Midland Basin. So each panel goes from 2012 to 2023. So you can see for 2012 to 2017 for my completions design, I have a big aggregate change in the performance, plus 15 or 20% just from that alone from upsizing my completions. But since then, that's been pretty flat. For geology, I have a big change from 2012 to 2017. Basically, as operators learn, hey, southeastern part of the basin has, on the whole, aggregate less rock quality. The northwestern part's where we want to be and where most of the drilling went. And that was kind of cruising along. And then in 2020 and 2021, rock quality shot up as operators high graded to their best stuff and didn't drill stuff that was uneconomic. And then that's kind of unwound a little bit over the past few years. Lateral length has actually just been going up and to the right the whole time. So as you look at, hey, what's changed performance over the last 3 years, completion design hasn't had a huge role. It's more been an interplay between increased lateral lengths and geology. And then spacing. Early time was a lot of parent wells, very wide spacing, production looked great. And then you've had a huge drop in the aggregate performance as operators have been down spacing and drilling more infills. And that actually more than cancels out the impact of the upsized completions. So this is just another way of looking at data and explanatory data that's coming out of these models and building your confidence in it, right? And then finally, quantifying uncertainty. And I think this is my last technical slide here, and my PDF conversion failed, which maybe this is maybe a good metaphor for the difficulty of quantifying uncertainty. But this is very useful, and it's something that people kind of expect. However, it's not as easy to quantify uncertainty for machine learning models as it is for a traditional analog type curve. So an analog type curve, you get your 45 wells that are your analogs. Here's my distribution of those. Here's my P10, my P90. Great. That's very straightforward, very easy. For these models, you have to get it's just more involved in doing it. So a lot of uncertainty quantification relies in some forms of bootstrapping, where you basically will do subsets of the data and see how much, including different subsets changes the forecast, as one example. And there's many different variations off of this or different ways to do it. You can also perturb input data. There's lots of ways basically that you can kind of try and get your way to it, but it's not quite as good as the standard method. But we do allow customers to do like, a P90 and a P10 or some other variable. And what we have found is some folks may, hey, we like to use a P40 for all of our AFEs just to bake in a little extra downside protection. Okay, that makes sense. Other folks maybe want to use like a P10 P90 ratio in some ways to risk adjust their inventory. So, hey, these wells look really promising, but they're a bit higher uncertainty than the other stuff, which is in the core of my position. So, maybe we shouldn't drill them, or who knows? But that type of a process is usually is often used by teams. And if my image had rendered here, you would have seen a nice P50 prediction, and then a P40 and a P60 and a P90. So you use your imagination. I think we got up to 500,000 barrels for my P90, which is fantastic. Well, for that one. Okay.
Very nice.
Yeah, that's it. Thank you. Happy to take any questions.
Do well.
Do well. Well, you can also, if you feel free to drop me an email. There's my email right there. We share a lot of stuff on LinkedIn, so you want to keep up on things. You can go follow us there. I'll be going to happy hour too. We got
The 80-20 split on data conditioning, are we moving towards a world where AI will be able to condition data for us? Or are you unleashing the beast a little bit there?
Great question. I'm sure Mike probably has some more informed thoughts on this than me. It's kind of, with the size of the data that we have in oil and gas. I don't know where my 80-20 went, but with the size of the data sets that we have, like, there might be some value in generating these synthetic data sets and using them as training. But you can't, I brought up this example earlier. Let's say you're trying to improve your cluster spacing. Maybe you have 800 wells of your own operated data. Let's say you're doing all right. You got 800 horizontals in the Midland Basin. I'd like to be there, but you might have only tried 40-foot cluster spacing and 60-foot cluster spacing, and no amount of synthetic data is gonna let you see what a 30-foot or a 70-foot cluster spacing would do on your performance. I don't know, Mike, you got any other thoughts on that?
And synthetic, it really just depends. Like, if you're looking at computer vision stuff, it's a lot less viable. Like the actual, images or video clips are way more important than creating the synthetic stuff. Tabular stuff, it's a little bit more viable, but to Ted's point, like, it's not there yet in terms of the synthetic creation that's going to make it as close to, the actual data. True data is better. But having said that, just over the last 4 years, synthetic data creation, at least on the computer vision side, has gone up significantly. It's allowed us to scale our algorithms, with some of the tough to come by data, especially well logs and things like that. But generally the 80-20 split is something, kind of a rule of thumb for most data science. But there's other tools like scikit-learn, like Ted was talking about, that will kind of adjust in an automated fashion, but you usually arrive around that split anyways. And the important thing is, post that is to test it in production and see if it actually works. And that's one of the things I was going to ask you was, is that something that Novi Labs does, is take the actual confidence scoring, or metric driven events, and then apply business rules, sanity checks, so to speak, to make sure that the data's trained properly.
We're not on specifically on the confidence interval outputs. We just kind of take those as they are, report them, and let our customers go place with them. Yeah, I mean, there's lots of sense checks and sanity checks built into the model, but yeah.
Yeah, that's great.
Yeah, I should say one other thing that we're thinking about, and this is just at the whiteboard stage for us, but we run like a little data network for our customers where they can pool their data for cluster stages and train models on it, without having to actually share or make the data visible to each other. And one of the things that we're discussing to make it more useful is to generate a synthetic data set off of that would have the same statistical properties without actually telling you, what Diamondback's cluster design was on this particular well.
Yeah, feature store. Awesome.
Anything else?
Have the ability to upscale issues due to vintaging, because I think, some of the issues that we run into is, early on, maybe completion styles were much different, and then through time, things have changed, and then when you go back into areas that were underdeveloped with old techniques, is there a way to take that rock data and kind of upscale it to see if you can kind of match or get more of a realistic EUR for the modern.
Yeah, that's algorithm. These types of algorithms can do really well at that type of stuff. So it's for our customers, that's a core use case. And one thing, we were discussing this week. You could put in the year when the well was completed as another variable to use as a training feature that would essentially let the models learn the kind of basin-wide learning curve, which that's another one that might give you very good results. And potentially, if you're trying to extrapolate out into the future, maybe you could use that, but that would take up a lot of the signal from the other completions variables. So typically we nudge our customers away from using a specific vintage year and more towards proppant intensity, fluid intensity, proppant type, stage count, stage spacing, frac rate, things like that, rather than the year.
That would be kind of cooked in like your formation or operator
Exactly.
data into it, so you're kind of double hitting it twice if you add in the year and the proppant intensity.
Yeah, exactly. It would make proppant look less important than it actually is, which could give you weird results out the other end. Yeah.
I'm a little curious on some of your data prep. I mean, you mentioned the linear regression models, and that's obviously good at identifying dependent and independent variables, but do you do any other more